let's look at the next topic, section 3.5, implicit differentiation. And then once we've learned that, we can use it to derive the derivatives of inverse trig functions. Remember, we've learned all the basic derivative rules, power rule, e to the x, product, quotient, trig functions, and now the chain rule. Let's just quickly review with a nice little warm-up exercise. All right, to take the derivative of this, we're going to use the chain rule a couple of times. Take the derivative of sine, leave the inside the same. Then take the derivative of the next outermost function, which is in this case the square root. Leave the inside the same. I keep writing 3. And then take the derivative of the next outermost function. And if we wanted to simplify that, which we wouldn't have to do for a quiz or an exam, but if we wanted to, then we would get this. So we have that, right? Chain rule, a couple of chain rules. This is important. We're going to be using the chain rule quite a bit. Now, we've always considered functions in the form y equals f of x, right? We look at a graph, it's in the graph y equals f of x. But there are actually graphs with more complicated things going on, right? We could have something weird like sine of x plus y equals y squared cosine of x. That is a thing, right? Or is that y squared cosine x or cosine of x, right? So if we go to Desmos right here, right? You have something kind of funky like that, right? Now this is obviously not a function of x, right? This fails the vertical line test. But it still is a function, and you can still talk about the slope of the tangent line. And in fact, it works exactly the same way as it did before, right? dy over dx is still the slope of the tangent line. So then the question is, well, how would we find dy over dx? So that's what we're going to learn, and this is called implicit differentiation. So I'll say right here, use implicit differentiation. What differentiation? Okay. What we're going to do is we're going to take the derivative of both sides with respect to x, still treating y as a function of x. Then we're going to solve for dy over dx. And the answer is probably going to be in terms of x and y, which is a bit different. But it will be correct. So, we're going to differentiate both sides with respect to x. Alright, so we get cosine, right? We take the derivative of sine, we leave the inside the same. And then we have to multiply by the derivative of the inside, which is 1 plus, now what's the derivative of y with respect to x? Well, by definition, it's just dy over dx, right? That's what we're solving for, okay? So anyway, now let's take a look at the next side, right? Well, here we have a product rule, right? This is one term, this is the other, so we need to use a product rule. Take the derivative of the first. Now, it's 2y, right? But remember, y is a function of x, so we also have to multiply by dy over dx, right? Pretend it was sine squared, right? You wouldn't just take the derivative of sine. You wouldn't just say it's 2 sine. It's 2 sine of x times cosine of x, right? So if that's a little confusing, then pause the video and think about it for a sec. And if it's still confusing, well, that's okay. Then just, we'll do a couple more examples, and it might make a bit more sense. Anyway, we take the derivative of the first term, we leave the second term the same. Now we leave the first term alone and take the derivative of the second term. Okay? Now at this point, we have to solve for dy over dx. Right? Well, just right there, right? So what we're going to do first is just simplify this a little bit, namely getting rid of these parentheses. Right? So I'm just going to write an imply symbol. Cosine of x plus y plus cosine of x plus y dy over dx. Right? I just distributed, right? Equals, and I'll keep this mostly the same. I think I'll tack on the dy over dx at the end just so it pops a little bit more. And I'll just make this a minus y squared sine of x. Now at this point what I want to do is I want to put all dy over dx terms on the left side and all the non-dy over dx terms on the right side. Right? So I'll just subtract this guy over. So we'll have cosine of x plus y dy over dx minus 2y cosine of x dy over dx equals, now I'm going to subtract this guy over to the right side, right? So it'll be negative cosine of x plus y minus y squared sine of x. Right? And then at this point, all we're going to do, move this up a little bit, is we're going to factor out the dy over dx from the left-hand terms, right? So it'll be cosine of x plus y minus 2y cosine of x times dy over dx equals, and I'm just going to just keep this guy, right? Leave the right hand the same. Alright, so then what does that mean? Well, we're running out of room here, so let's maybe shrink this a little bit. Alright, so what that means then is that our answer is going to be dy over dx equals, and it's just this guy again, divided by the thing we factored out, right? Cosine, just divided by the rest of the left hand. Right? So that's our answer, right? Believe it or not, this is our derivative. And if we wanted to know the slope of the tangent line at any point, x comma y, then we would plug in x comma y in for x and y into this expression. And we would get a number, and that would be our answer. Right? And the process of differentiating both sides of an equation, again, is called implicit differentiation. Now note that the chain rule is extremely important because any time we compose y with a function, we have to also multiply by the derivative of y, which is dy over dx, for example, with y squared, right? The derivative wasn't just 2y, it was 2y dy over dx. I'm going to continue to use dy over dx, but you might see in the textbook that you might see them use y prime. It's another way of writing dy over dx, just a heads up. Alright, so example 3. Alright, let's look at another example. It's a little bit nicer. Find the equation of the tangent line to this curve at the point 2 comma negative 11, right? So let's again implicitly differentiate. Right, so we have 2x. Now be careful here, right? This is actually a product rule right here. So it's going to be 1 times y plus x times dy over dx, right? Because we took the derivative of y with respect to x, minus, now remember this is not just 2y, it's 2y dy over dx. The right side's a bit easier, it's just 0. Right? So now at this point we want to clean this up. All the dy over dx terms can stay on the left side, everything else goes to the right. So we're going to have x, I'll move this over a little bit, x dy over dx minus 2y dy over dx equals negative 2x negative y. And then this, look, we're going to factor out the x minus 2y. The dy over dx, right? And then at this point, we just divide. Alright, just cross it out. Okay? Well, maybe I'll do it this way. And then cross it out. Right? Cross it out. So that's our answer. Well, it would be, except remember, it's at the point 2 comma negative 11. So here we have to write, we draw a vertical line and write x comma y equals 2 comma negative 11. Right? Yeah. But I actually don't think that's quite right. I don't know why I said negative 11. 2 comma negative 11. Hold on a second. If I plugged in 2 negative 11, I get 4 minus 22 minus 121. So actually, sorry, this is a little bit of a technical thing right here. This should be negative 139 for that to be true. Okay. Sorry about that. Need a little correction right there. Anyway. What are we going to get here? Okay, so anyway, we plug this in, and we're going to get, let's see, negative 2 times 2 minus negative 11 all over 2 minus 2 times negative 11. And that's going to give us negative 4 plus, I think it's 7/24. So that's our answer, right? Well, no, not quite. So the tangent line has equation y minus negative 11 equals the slope, 7/24, times x minus 2. That's our answer. Okay. And let's just do a couple of examples. Alright, let's take a look at this guy, right? Cosine of xy equals 1 plus sine of y. Well, let's see, we're going to do negative sine, remember, leave the inside the same, times, I'm just using brackets, you can use parentheses if you want, it's the same thing, x dy over dx plus 1y equals cosine of y dy over dx. Right, and this gives us, negative x sine of xy minus y, negative x sine of xy dy over dx minus y sine of xy equals cosine of y dy over dx. Alright, and remember how we always do this, right? We're going to subtract over this term, add over this term. So we get negative x sine of xy. And I'm just going to go ahead and factor them out, right? I'm going to save a step. We've got a lot of problems ahead of us, right? Factor them out, factor out the dy over dx. Do that in one step, right? Save yourself a line of work. And then just divide by it, right? And we're done. Maybe I need a little bit more space. Alright, and we're done. So that's our answer. This one's a little bit nastier because it's got a quotient rule in it, but we can still do it, right? Left hand. And then multiply by derivative of the inside. Equals, and now we just have to do the quotient rule, right? 1 plus x squared times dy over dx minus high d low all over low squared. Yeah, kind of gross. We can make that look a little bit nicer, right? We simplify this and we'll get secant squared minus secant squared, right? And then this is going to equal, so what I'm going to do is I'm going to split the fraction and then cancel one of these just with this first term, not with the second, okay? So it's going to be 1 over 1 plus x squared dy over dx minus 2xy over 1 plus x squared squared. So at this point, same thing as before. See how this requires a bit of work, but it's very formulaic, right? We're going to get negative 1 over 1 plus x squared minus secant squared x minus y dy over dx equals negative secant squared x minus y minus 2xy over 1 plus x squared quantity squared. And then just divide this gross thing out. In fact, I'm just going to go ahead and kind of cheat a little bit and copy paste this bad boy. Bad boy right down there. Maybe rotate that a little bit. And then there you go. Right? And by the way, if you don't like all these negative signs, well, you can just multiply the top and the bottom by negative 1. And there you go. Right, you just get that. Right? Let's do one more practice problem. Product rule equals product rule, right? Look, dy over dx. Sine plus y cosine, and then times 2, right? Remember the chain rule, equals 1 cosine of 2y plus x times negative sine 2y times 2 dy over dx. See why? Right, and then all this is going to equal, right, or what this is going to imply, right, again, get those dy over dx's on the same side. Sine of 2x, and this is going to be plus 2x sine of 2y because we're subtracting over the negative. And this is going to equal cosine of 2y minus 2y cosine of 2x. And then we just divide by all of this. Copy. Paste. Right down there, right? Draw a line, cross it out, and that's our answer. So again, it's a bit of work. It might be a lot of work, but it's always the same. Implicitly differentiate, take the derivative of both sides with respect to x, put all the dy over dx terms on the left side, factor out the non-dy over dx, and then divide. And that's your answer. Okay? And that's how we do that. Alright. Now next up, a little bit more implicit differentiation, right? We're going to get into derivatives of trig functions now, right? But if we just recall this problem, actually, why don't you go ahead and try that one? We've done a lot. Okay. Now, when we talk about inverse trig functions, right? We're talking about going backwards. We're not talking about 1 over. We're just talking about going backwards. Okay. So we have, for example, arc sine of x, or you could write this as sine to the negative 1 of x, but that's not really preferred, so I'm going to use arc sine, is defined as the function such that arc sine of sine of x equals x, and sine of arc sine of x equals x. Right? So they undo each other. It's like the square root of x squared. Right? It equals x. So remember, sine of an angle gives you a number. Arc sine of a number gives you an angle. So for example, if sine of pi over 4 equals root 2 over 2, which we all should know, then arc sine of root 2 over 2 equals pi over 4. Alright, so just a couple things about these functions, blah, blah, blah. Just to kind of show you using Desmos here, right? Just y equals, that's the graph of arc sine. That's the graph of arc cosine. And then it's the graph of arc tangent, right? So just to kind of quickly show you, that's what we're working with here. Got this super quickly. There you go. Anyway, a couple of quick simplifications here. Cosine inverse or arc cosine of root 2 over 2, that's going to be pi over 4. Arctan of 1, that's actually also pi over 4, right? Because it's arc sine of 1 over arc cosine of 1, right? Or sorry, I shouldn't forget I said that. No, I lied. That's not true. It's the angle at which sine equals cosine, right? The angle at which tangent equals 1. When does tangent equal 1? It equals 1 when sine equals cosine. That's pi over 2, right? They're both root 2 over 2. And then, of course, this is just x. We should know that. Okay? Now, it turns out that this is true, right? We use implicit differentiation to take the derivatives of arc sine, arc cosine, and arc tangent, and their derivatives are maybe something that we didn't quite expect. Right? Now, how do you prove these? Well, I'll prove one of them for you, and I'll let you prove the others, because they're very similar. Okay? Here's the proof. We want to show the derivative with respect to x of arc sine of x equals this. How do you show that? Well, we don't know anything, right? We're going to consider y to be arc sine of x, right? We don't know anything about arc sine. We don't know its derivative. So that's not helping. That's not helping anything. However, we can apply sine to both sides, and we get sine of y equals sine of arc sine of x. And by definition, we know that that equals x. So sine of y equals x. That is important because we're going to implicitly differentiate. So we're going to get cosine of y, dy over dx, equals 1. Well, if we can solve for dy over dx, we're going to get dy over dx equals 1 over cosine of y. Well, that's not very helpful, right? We want our answer in terms of x, right? Y equals arc sine of x, so we want our answer in terms of x. Well, it turns out what we can do is we can think of a right triangle and we can say, hey, consider an angle theta. If y equals arc sine of x, or maybe I should say, instead of angle theta, I should say angle y. Let's say y, actually, I guess, right? Thomas, please finish up your exam. Hold a sec. Thomas, please finish up that exam in the next minute. What we've got here is if we know that if y is our angle, arc sine of x is just opposite over hypotenuse, right? Sine is opposite over hypotenuse, right? If sine of y equals x, I guess it's probably easier to look at this, right? If sine of y equals x, then we know that that's true. And if we use the Pythagorean theorem, right, we know that a squared plus x squared equals 1 squared. So we know that a winds up equaling square root of 1 minus x squared. So actually, this winds up equaling the square root of 1 minus x squared. So the derivative of arcsine is 1 over square root of 1 minus x squared. So for these guys, I'll just say try them. Try doing them yourself. It's very similar to what we did before. Okay?